Hi! In this video, we'll be continuing our journey in real analysis, and today we'll talk about the criterion for absolute convergence. So, in the previous video, I went through what is absolute convergence and how it's being applied to show that if your series converge absolutely, then your original series converges sequentially. And today we'll show when we use absolute convergence to help us in proving that a series converges absolutely. And so it says that if your terms of a sequence is dominated by this Cn, so Cn is like this positive sequence because this is greater than 0. So your terms of the sequence, the absolute value, are all dominated by this larger positive sequence that converges absolutely. Then your original sequence converges absolutely as well. And part B of this comparison test says the contrapositive. If now you have a sequence that diverges and all these sequences are positive, then your series will diverge. It does not converge absolutely, basically. But it doesn't mean that since it doesn't converge absolutely, it doesn't converge to a limit under a rearrangement of terms. And I'll talk more about that in a subsequent part. But just know that this series will diverge. So the proof is given as follows. You're given an epsilon. You know that there's a cutoff such that Cn, Ck, the sum from n to m, will be less than epsilon due to the Cauchy criterion. And hence, this term you can now replace each of these Cn's with Ans, and it will still be true because the absolute value of the sum from n to m of ak will be less than this due to triangle inequality, which then will be less than ck because each of these terms in ck dominates an. And hence, this will be less than epsilon, and so an converges. It also shows that an converges absolutely. And so part B, you can just prove the contrapositive because now we know an dominates dn. So if an converge, then dn converge. So the contrapositive is dn diverge, then an diverge. And we're done. And so this comparison test is really very useful because it gives you a way to now make use of series that you know to bound your original series that you want to show converges. And with that, you just need and then this series that you bound is easier to show whether it converges or not. And we'll see examples about it for you to better understand. And one more thing to take note is the idea of this limit comparison test, which says that if x and y are positive sequences and this limit exists, then if the limit isn't 0, xn is convergent if and only if yn is convergent. And if x is equals to 0, then yn is convergent, meaning this approaches a value, then xn is convergent as well. And it should be known that xn equals to 0. So it follows that The idea follows from an exercise in a textbook, but I'll give you the main idea. It follows that if this limit exists, now you can bound yn in xn in between yns, and then you use the limit comparison to test to show that if xn converges, yn converge, and if xn diverge, then yn must diverge as well, and you're done. And if r equals to 0, then you know there will be a term where yn always dominates xn, and so only if yn is convergent, then xn will converge. So with these two tests, now we will see more examples about it. And one example is the series 1 over n squared plus n, the sum of it. And it's quite clear that 1 over n squared is less than 1 over n squared plus n is less than 1 over n squared, because you're getting a larger denominator. And we know that this series 1 over n squared is convergent, and so by the comparison test, it means that 1 over n squared plus n is convergent as well. And we see a use of the limit comparison over here, because in this case we can't really bound it with 1 over n squared, and so instead we can just take xn to be 1 over n squared minus n plus 1, and yn to be 1 over n squared, so that when you take the quotient of xn over yn, you get the following, which has a limit approaching 1. And therefore, because this limit exists and is the convergence of the series follows from the limit comparison test. Since you know 1 over n squared is convergent, this means xn is convergent. And you can see how by using a pre-knowledge of many types of series, you'll be very useful in using the comparison test. And so what's the study is that this is why the common series known as the P series is very useful for this purpose. And what is the P series, you might ask? Well, basically 1 over n squared is the 2 series. So 1 plus 1 over 2 squared plus 1 over 3 squared plus all the way. This is known as the 2 series. Then 1 over p, the P series is 1 plus 1 over 2p plus 1 over 3p plus all the way. So it's the power of p. And now we will show when the P series diverge or converge. But to help us prove that, we need to first prove this other test that we can do, which really actually makes use of the comparison test, but it's now how we bound the sequence. And so let's say we have a decreasing positive sequence. So A1 is larger than A2, and so on. Then the series converges if and only if this new series converge. And this is known as the Cauchy condensation test. And so you're really just taking like the even terms and multiplying it by a coefficient. And the proof follows because if n is less than 2k, so n is less than 2k here, then the partial sum will be a1 plus an all the way to a2k plus 1 minus n. Minus 1, I mean. And this whole thing will be less than a plus 2a2 plus all the way to 2k a2k. And that's because a plus a3 is less than a2, so you can group them. So you just keep grouping them all the way. And as a result, this will be known as tk. So it's over like over here. And so Sn will always be less than or equals to tk for n less than 2k. And if n is greater than 2k, we see that Sn is actually greater than half tk. And so in all situations for any n, Sn will be bounded between Tn and half Tn. And so the series Sn converge means Tn converge, and then Tn converge means Sn converge, and we're done. And so the P series, the sum of 1 over P n to the power P, converges if P is larger than 1 and diverges if P is less than 1. And that's because if P is less than 0, then this term just gets infinitely bigger, and so it diverges. If P is greater than 0, then we can apply what we use the Cauchy condensation test to show that the series now, we can consider the following series over here, and this equals to this geometric series, which converges if and only if 1 over 2 to the power of 1 minus P is less than 1. And this is only true if 1 minus P is less than 0. And hence, it proves the following result. And so, that's all for this video where I went through the comparison test. We'll see more tests to show the convergence of series in the next video. So, stick around and I'll see you again. Bye.